There we go. Everybody, I'd like to thank you for coming to today's seminar. Today, we're going to hear from Yoo Min Park from East Carolina University. And she's got some very interesting work that I'm sure you'll find interesting. I've asked our very own Dr. Eric DeMel to introduce Yoo Min as a fellow spatial epidemiologist and take it away, Eric.
Okay, thank you, Doug, and welcome the students who join us as well and other faculty members, I can see. So yeah, it's my pleasure to introduce Yoo Min Park. And so a little bit of a text or introduction text to read, I think, to make justice to her work. So I know of Yoo Min Park from the Health and Medical Geography group at the American Association of Geographers, where she quickly rise as an excellent scholar while she was doing her PhD. In fact, she did get her PhD from the University of Illinois Urbana-Champaign, so UIUC, I believe with Mepo Kwan. So some of the students here on the Zoom meeting know of Mepo Kwan's work, and so I think it's some of these very solid health geographer, and Yoo Min is an excellent product from that movement. She earned her PhD in geography, so from there, and also a master and bachelor degree from Korea, South Korea, at Korea University in Seoul. For doctoral dissertation, she focused on space-time approaches to better understand the environmental justice and multi-contextual segregation. That work was recognized at the American Association of Geographers, where she received the Jacques May Prize for the best dissertation in the team of health and medical geography. And every year, the group awards or opens the competition and awards one prize per student. And so it's pretty remarkable what she has been able to do. So as part of her research, she focuses on, as you probably can tell from the title, to understand environmental health, environmental justice, and health disparities using geospatial technologies or GIS, and of course, spatial statistical methods. And I think that her work speaks a lot to my class in medical geography when we talked about exposure and movement of individuals and the sort of static approach that is not correct when we talk about exposure. And I think her work really fits nicely in there. She co-designed the GeoAir 2. So it's a wearable air quality monitor. She utilized high resolution environmental data and people travels pattern, again, something that we talk in medical geography, to identify how individuals interact with environmental and social factors when they move through multiple microenvironments, and where that the scale is important. So I forgot to mention when I introduced Yoo Min Park that she's currently a faculty member at East Carolina University and as an assistant professor, where she's in the Department of Geography, Planning, and the Environment. She also directs a lab there called the GeoHealth Lab, where health disparities are investigated using geospatial technologies, GIS, of course, community engagement, the qualitative part I've talked to many students about, and of course, spatial statistical method, which is more on the quantitative side. So she's using mixed method in a way, or that's her approach. And her work has been supported by different agencies, such as NSF, the National Institute of Environmental Health Science, and NIH as well, and also AAG, but NIH is really big, so we have to mention it. So today we'll hear from Yoo Min Park, or Dr. Yoo Min Park, rather, in her presentation on personal exposure monitoring using GPS-enabled portable air pollution sensors, a strategy to promote citizen awareness and behavioral changes. But before I pass on the floor to you, Yoo Min, I really want to thank you for taking a little bit of your time in a busy schedule to share, your passion to the field, to us. And I know you have probably classes to teach it too, so we won't take too much of your time.
You're welcome.
But it's really a really good opportunity for us to learn, about your research. So thank you and welcome, even if it's virtual.
Thanks for the great introduction, Dr. Demler. And also I want to thank Dr. Shoemaker for inviting me to talk about my research at this virtual seminar. And thanks everybody for joining my presentation today. Let me share my screen. So you can see it. Can you see it?
Yes, we are
go
good.
ahead.
Yes, we are good.
Okay.
Yes, you can go. If there is any problem, I will interrupt you, but it's all good. Yeah.
Okay. So I'm gonna talk about my major project I've been doing at ECU. So my presentation title is Personal Exposure Monitoring using the GPS-enabled portable air pollution sensors, a strategy to promote citizen awareness and behavioral changes regarding indoor and outdoor air pollution. So what I'm going to present today is a part of my interdisciplinary pilot project titled A Low-Cost Mobile Air Pollution Sensor with Geospatial Mapping, a tool for community engaged environmental health disparity research. So this project was supported by the Center for Human Health and in the Environment at North Carolina State University, and also supported in part by the National Institute of Environmental Health Sciences of the NIH. So as a PI of this project, I've been collaborating with Dr. Sina Sozan in public health and several student researchers in geography, environmental health, science program, and public health. And I've been also collaborating with the Association of Mexicans in North Carolina, which is a nonprofit organization. I'm Mexican for this project. So before I dive in, let me give you some background for this research project. The air pollution is known to cause many cardiovascular and respiratory diseases like asthma or heart attacks or lung cancer, and even premature death. But one of the hardest things about protecting our health from air pollution is that we can't see it. So we can't see air pollutants around us because they are typically extremely small. So among many different air pollutants, particulate matter, especially PM 2.5, is known to pose greater health issues due to its small size. So PM 2.5 is, just simply speaking, a fine dust pollutant. It's particles with diameters that are smaller than 2.5 micrometers, which is about like 30 times smaller than human hair. So because it's extremely small, it can get deep inside your lung when you breathe it in and can cause serious health problems. But when you look at the spatial distribution of particle pollution, you can notice that low income and or minority communities tend to bear unequal burden of air pollution because many of them live near polluting facilities or busy roads with heavy traffic. But this disparity is not just limited to where they live. So where they work, where they do leisure activities might also been environmentally less favorable than where high income or dominant groups do. But we still don't know much about how they face greater exposure to air pollution during their daily activities in various indoor and outdoor environments. Why? Because there may be several reasons, but I'm going to talk about three major reasons, I think. So first of all, so most exposure and health risk assessment have been based exclusively on data drawn from ambient air monitoring networks. So, but these air monitoring stations are too dispersed over the large area to capture local variation in air pollution concentrations. So as you can see in this map, there are only 22 regulatory PM 2.5 monitoring stations in North Carolina. But PM 2.5 concentrations vary dramatically over space and time. So it varies even street by street or changes even every second. So with these few stations, we don't have enough data to know local air quality that we encounter in our everyday life spaces. And because we can't put that giant air monitoring station inside our home, right? Or any other indoor spaces. So most previous studies have focused heavily on assessing exposure to outdoor air pollution, probably simply because there's just no indoor air quality data. But some recent studies suggest that indoor air could be like 2 to 5 times worse than the outdoor air, even in large cities that are highly industrialized. And we spend most of our time indoors, so the health risk associated with indoor air pollution may be higher than those associated with exposure to outdoor air pollutants. But while the problem of outdoor air pollution has been widely studied and regulated, indoor air quality has gained much less attention in the literature and is largely unregulated because of this significant knowledge gap, like preventive measures to reduce exposure to indoor air pollution have been limited. So in my research, I argue that this discrepancy in the attention given to controlling outdoor and indoor air pollution can be partially explained by the difference in the levels of public awareness about outdoor and indoor air pollution and associated risk perceptions. So some recent studies have begun to place low-cost air sensors inside people's homes to measure home air quality and increase like public awareness of indoor air pollution, which is a good step. But the problem is we don't stay at home all day long, right? So the studies that focus only on measuring home air quality using a stationary sensor do not provide a full picture of exposure that people experience in various outdoor and indoor environments, like at their workplaces or churches or restaurants. So it often fails to satisfy people's curiosity. So the lack of comprehensive data and the invisibility of air pollution makes it difficult for people to act in informed ways to reduce their exposure, both indoors and outdoors. So people tend to be more motivated to alter their behaviors when they are offered personalized information about their risk and informed of the air quality in their immediate surroundings. So, and if these highly localized and personalized air pollution data are combined with other data sets like location data or activity diaries, then they can significantly enhance an understanding of the effect of places and activities on personal exposure to air pollution, because this information will allow people to make connections between their activities, activity locations and time, and resulting changes in air quality. So this can help them maybe better identify possible ways to reduce their exposure. So it's important to monitor both indoor and outdoor air pollution at a fine granularity to better understand spatial temporal variations in exposure, improve citizen awareness, and promote behavioral changes to reduce overall health risk associated with air pollution. So to address all these limitations, first of all, we should be able to measure the air quality in our immediate surroundings, both indoors and outdoors. And we should also know where people stay and what activities they perform there. Fortunately, recent advancements in air sensing and positioning technologies have allowed us to do this. So over the past decade, these technologies have been rapidly evolving. So air monitors have become much smaller, lighter, and cheaper. So now we can involve citizens in real-time air quality monitoring and collecting both highly localized air pollution data and people's location data, which is really exciting and promising, right? And there are so many options we can choose in the market, but here is a big but. Unfortunately, none of these commercially available devices met my research needs because most devices do not have all the components and all the features that are necessary for citizen engaged geospatial assessments of personal exposure, especially for scientific research that aims to engage with vulnerable and socially disadvantaged communities. For example, devices designed to mainly target the general public do not provide sufficient accuracy for credible data or lack the elements required for scientific research, like data lockers. And so they are kind of like just for like entertainment, in my opinion. And most of them are not portable because there's no built-in GPS or internal battery. On the other hand, devices that are widely used by researchers and scientists may provide more accurate data, but they are often not really ready for citizen science applications because they are technically too complicated to manipulate. For example, many of them require like a connection to local Wi-Fi network or a constant Bluetooth connection between to a user's smartphone or external GPS locker to view or store air pollution data and collect GPS data. But then what happens when the Bluetooth is disconnected? Data are lost. So some previous studies reported all these issues, including my paper here. So smartphone applications paired with these sensor devices are often not reliable and crash, causing data loss and participants of frustration and high dropout rates from the study. And many of these mobile applications work only on an Android phone and do not work properly on low quality smartphones. That means it limits the eligible participants to only a subset of the population, right? But like not everyone has a strong internet connection and has a good Android phone and is technically capable, right? So these local sensors have been deployed mostly in communities with a good Wi-Fi network. And many studies that use this kind of technology have often excluded most vulnerable groups or marginalized communities. And I think this ultimately may exacerbate environmental health disparities. So very few empirical studies have evaluated how citizens respond to air sensor technologies and whether using sensors leads to changes in their awareness, attitudes, and practices regarding indoor and outdoor air pollution, especially among members of the underrepresented communities. So all these challenges I mentioned right now are actually what I recognize through my previous research experience when I was a PhD student at the University of Illinois. So our research team had many great research ideas, actually. We were so excited, and then we collected personalized air pollution data from a low-income community in Chicago using a portable air pollution sensor. But even though we choose the best portable air pollution monitor that was most popularly used by researchers back then, we encountered several challenges in collecting reliable data and effectively engaging with the participants and had to deal with a lot of troubleshooting. So when there's no perfect research instrument for your research, what can you do? Well, you may have to make your own, right? If you have money, right? If you have money. So I was fortunate to receive funding from ECU to develop a new standalone GPS-enabled portable air monitor that meets all my research needs. So based on the lesson that I learned from my previous research experience, I designed it to address all the limitations that I identified. But I'm a geographer, right? I don't really know much about electrical engineering, so I contracted out for prototyping and manufacturing. And my husband is someone who is doing electric stuff as a hobby. So he helped the smooth conversation between me and the company. So this new device is my major research instrument and brought a lot of interesting collaboration opportunities within the US and across the world too, and has been used in my major research project that I'm presenting today. So this device is called GeoAir because it collects georeference air pollution data in real time due to its ability to track user locations through the built-in GPS. And because the data is georeferenced, we can visualize the air quality data on a map and analyze it to estimate personal exposure levels using GIS and geospatial methods. So it is also suitable for citizen engaged research because it's really easy to use. So GeoAir does not require a connection to a local Wi-Fi network or a constant Bluetooth connection to a user's smartphone, or have to rely on like smartphone application, which is not reliable, because it has an internal data logging capacity and display screen. So you can really ensure participant diversity and inclusivity. So GeoAir records PM data every minute, as well as GPS locations, and a list of nearby Wi-Fi MAC address for indoor geolocation, temperature, humidity, data, date and time, and more. The data are stored locally on a micro SD card as an encrypted file for data confidentiality. And for more details, please see my paper published last year. So my collaborator at ECU has already tested the sensor performance and scientific reliability in both laboratory and field settings. And the results show that the GeoAir data are highly correlated with reference instruments. So it provides sufficient accuracy for credible data for scientific research. And researchers in Belgium have also been testing GeoAir in laboratory and field settings in Belgium as either stationary or mobile monitor for 3 months so far. So I'm really curious about their results too. So now let me talk about how GeoAir has been used to address my research questions. So from now on, I'm gonna talk about a portion of my project, which is actually currently under the second round review by a journal. So there are two goals of this part of this study. First, it seeks to identify the locations and times at which Latino and Hispanic people experience high exposure, and the activities that lead to pollution peaks by combining their georeference air pollution data and travel activity diaries using GIS. Second, it aims to examine whether georeference air pollution data collected using portable monitors coupled with travel activity pattern data improve the community's awareness of indoor and outdoor air pollution and foster behavioral changes. So for these goals, so we have been engaging Latino and Hispanic communities in Eastern North Carolina in participatory air monitoring in partnership with the Mexican. So many Latinos in this region, in this Eastern North Carolina, are recent immigrants who have moved for employment. And many of them work in highly polluting industries like construction, restaurants, or manufacturing and agriculture, and live in manufactured housing too. So involving this community in air quality monitoring is crucial because its members are often underrepresented in environmental health research and policy decision-making processes. So we use GeoAir for this study. I'm not going to repeat because I already explained all the unique features of this device. So my husband was willing to be a model for these pictures, although he was a little sleepy when I took these pictures, so I had to be really quick. So it's portable, just like it looks like this, portable and wearable using a belt clip or a carabiner or shoulder strap like this. So those are actually the accessories that we provided to participants too. And for this study, we developed a web-based travel activity diary too. The benefit of using a web-based travel activity diary over a paper-based one is that people can access and complete the diary in real time using their smartphone. So this can significantly reduce recall bias. And using this diary, people were asked to record all the places they visited or stayed and the activities they performed in those places and like the exact time they started the activity, etc. We also obtained a basic demographic information about what's going on. Okay, our participants, including like gender, age, educational attainment, household income level, employment status, occupation type, smoking status, like that. And participants also provided the physical addresses of their homes and workplaces or schools. Lastly, we conducted surveys on people's awareness and behaviors regarding indoor and outdoor air pollution. So there are 3 thematic areas in the survey: knowledge, attitudes and perceptions, and behavioral intentions and practices. So during this study, participants completed this survey twice, like before and after the air pollution data collection using GeoAir. I mean, like participants completed pre-session survey during training and a post-session survey with the same set of questions for like 4 weeks after data collection. So for this project, by collaborating with a Mexican, we recruited like 51 Mexican people, and then we co-developed training materials to make sure they are culturally and linguistically appropriate. And among 51 people, 45 people were enrolled in the study, and 44 completed all the tasks we requested. So, and we co-organized multiple in-person and virtual training sessions. And during these sessions, participants completed a demographic survey and a pre-session survey about their awareness and behaviors related to air pollution. The participants were requested to do the 2 things for 3 days, like 2 weekdays and 1 weekend day. First, carrying the GeoAir device. Second, completing the web-based activity travel diaries for 3 days. So once the air monitor was returned, then we analyzed their data as soon as possible, and then we mailed a printed copy of data analysis visualization results to each participant. After they received the results, we had a meeting with each participant to enable them to actively participate in data interpretation as citizen scientists. So during this meeting, they provided us with valuable additional details about their data by recalling specific events that occurred during the data collection, which they thought could be the potential sources of air pollution like that. So they also offer critical insights into the data analysis results based on their knowledge of the community's culture, social networks, and economic conditions like that. So for 4 weeks after the meeting, participants completed a post-session survey with the same set of questions as those in the pre-session survey. And finally, we conducted also like a follow-up interviews with selected participants to further understand how they felt about the portable air monitor and their data and the data visualization products, as well as whether they felt that the method used in this study promoted their awareness and behavior changes too. Okay. So let me talk about what we did to analyze and visualize participants' data. First, data integration using GIS. As I said, GeoAir collects both GPS and a list of nearby Wi-Fi MAC address data every minute as location data, right? So what is a Wi-Fi MAC address? It's a unique ID assigned to each Wi-Fi device at a factory. So I use this data to restore the geographic coordinates of visited locations captured inaccurately by GPS. But geolocation using Wi-Fi MAC address is not a new idea, right? So as Google and Apple have been using it for more than 10 years. And their primary use is to provide location data to devices that do not have GPS, or to get a quick location fix when getting a GPS fix is slow. So if you send your Wi-Fi MAC address data to Google, then they will give you the approximate location assigned to that particular Wi-Fi MAC address. But the novelty of my method here is that we do geolocation offline using a fusion between GPS and Wi-Fi data without using a third-party service like Google, which is not free, and without the privacy implications of sending participants sensitive location data to a third party. So another benefit is that underserved or remote or low-income communities might be poorly mapped by commercial services. Like, I actually tested some MAC addresses in my own route, but a good number of MAC addresses were not found in the Google database. So usually when we lose GPS signal, it's because we entered an indoor location, right? It stayed there for a subsequent amount of time, like at home or workplace. So for those, we need the help of the Wi-Fi MAC address to identify a location. So look at this visualization of 4 randomly selected individuals with 3-day location data. The red is when there was no GPS fix, and green indicates when there are a GPS location acquired. For some people, they had pretty good GPS data for almost a whole time of the study period, while others have some like lost and inaccurate data, GPS data occasionally, especially when they stay at home or other enclosed spaces. So first, what we wanted to do here is to assign each MAC address that we found at fixed indoor locations to one set of geographic coordinates. Of course, some MAC address might be mobile, like a Wi-Fi on a bus, but for those MAC addresses, there's no location information because it's mobile. And if a MAC address is associated with area that is too broad, then we excluded those addresses. Otherwise, we calculate the average location for that MAC address. So now by doing so, we have a location assigned to each MAC address in our data. And then to automatically label data points as either stationary or in transit, we check if the set of MAC addresses the device captured did not substantially change for at least 10 minutes. And we use the Wi-Fi database that we just created for only stationary data points where we didn't have good GPS data. So first data source should be GPS, and we use this Wi-Fi database as supplement data. So we calculate the average coordinates of the 2 most frequently captured MAC addresses to estimate a location at that particular time, as long as those 2 MAC addresses have similar coordinates. And when we manually checked these inferred locations by comparing them with participants' travel diaries, we identified that they reasonably corresponded to each other. So I'm writing a paper about this method actually. So you may be able to find some more details about this method if it's published. But the bottom line of this method is that it works better in rural areas than third-party services, and it's free because we didn't have to pay a third-party service, and it makes the IRB happy because we didn't have to say we're going to share participants' data, sensitive location data, with a third party like that. So, and then I developed a method for automatically classifying each location into different place types, like a homes, workplace, other place, and in transit like that, using geocoded home and workplace addresses. I then combined the outcome of this method with travel activity diaries by matching times and locations using GIS to visualize and analyze personal exposure by place type and activity type. So using the final outcome, we calculated the summary statistics for PM2.5 concentrations in each place type, and then created these 2 time series graphs for each individual. So one visually links the type of microenvironments participants stayed and the activities they conducted in each place and the corresponding PM2.5 concentrations. And so the activity markers were placed on this graph based on the activity start time. And the other shows the PM2.5 concentrations and corresponding health concerns. And for visualization purposes, any PM2.5 concentration exceeding 500 microgram per cubic meter were replaced with 500 to improve the readability of the graphs. So we also create a map to highlight the spatial variations in concentration along people's movement path, but for data confidentiality issues, I didn't include those maps in this presentation. So these results were what we shared with our participants for meeting. And finally, we performed paired sample t-tests to compare the mean scores between the pre and post sessions for each thematic area to evaluate participants' changes in awareness or behaviors related to air pollution before and after the intervention. So now let me talk about what we found. So on average, people spend 75% of their time at home, 9% at workplace or schools, 5% in transportation, and 11% in other places. And you can see the locations categorized as other places had the highest mean and standard deviation values in PM 2.5 concentrations. So the activities performed in the other places include performing civic or religious activities, eating out, using drive-through services, shopping, and using a private car service like that. So it means that various activities and sources in recreational, or religious, or social venues, or other public buildings produce PM 2.5 over a wide range of values. So, and home location had the second highest mean and ST. So this means various pollution generating activities occurring at home, as well as different level of availability of preventive measures, like between households, like ventilation systems. But almost all participants here had low levels of exposure during traveling. It may be because air quality in Eastern North Carolina communities are not as poor as in big cities or on typical days, or it may be because many of them might have driven cars with windows closed. All right, now let me show you some examples of individual exposure profiles to further demonstrate the effect of places and activities on personal exposure. So first of all, we found that the individual's daily exposure profiles are widely different, even if they live in the same home, like a married couple, depending on where they stayed throughout a day and what they did in those places. So these graphs are actually made in Spanish because these are exactly what we shared with each of our Latino or Hispanic participants, except a few who prefer English. But for this presentation, I just replaced some important text with English, like the titles of the graphs or legends. So for each participant, we provided these two time series graphs like this. And we found that most participants experience PM 2.5 peaks indoors rather than outdoors when they perform activities that generate particle pollutants without adequate ventilation. In many cases, the timings of many high peaks in participants' data corresponded to when they were cooking at home, like just like you see in this person's graph. So for this person, there are two peaks, and both peaks happened when the person was cooking at home. And when we had a meeting with each participant, several participants reported that many traditional Mexican cuisines include frying, grilling, and they observed a significant amount of smoke and high readings on the air monitor while grilling steaks, frying tacos with oil, cooking Mexican chorizo using an oven, and burning food. So such oil-based cooking typically emits very high levels of fine particles. I mean, we cook every day to make food to eat, right? But unfortunately, the data tells us that cooking is a major contributor to the high levels of PM 2.5 in our home. But when we looked at another person's data, we identified another source of indoor air pollution. So this person told us that they were gathering around the fireplace at home at the time of the air pollution peak, which exceeded the hazardous level. But how many of you have ever thought about hair dryer can also generate such hazardous level? So this participant told us that she clearly remembered when she saw a very high value on the air monitor screen when she was drying her hair using the hair dryer. So I found this result really interesting and made me curious about like whether my hair dryer is okay and whether I need to clean the filter, because I've been very lazy to clean the filter in my hair dryer. So although it was not presented in this graph because the maximum value in this graph shows is 500 microgram per cubic meter, But actually the PM 2.5 levels was more than 2,000, which is extremely high, given that the guideline value for the hazardous level is only 250. And one participant experienced multiple sharp spikes in PM 2.5 at his home and office too. And what happened? So it wasn't clear when we looked at his data because his activity diary data didn't tell what was going on at those peaks. So activity markers were not placed at the peaks on the graph due to incomplete travel activity diary data. But through the meeting with him, we learned that he smoked a lot and he often burned incense sticks at home. But some people experience the highest pollution peaks at their workplaces. So this person works in the construction sites, and a pollution peak was observed when they were cutting bricks at work. And this participant has a job in furniture refurbishing. So he has also experienced the highest exposure levels when he was removing old paint from furniture. This person also works at a dry cleaner where he was exposed to unhealthy or very unhealthy levels. But what I found most interesting is that 4 people were exposed to unhealthy to hazardous level of PM 2.5 during mass at churches. People told us that it was because churches were burning incense or candles as an important part of religious ceremonies. So it means that people who spend extended periods inside poorly ventilated churches, like church workers or worshippers who frequent churches, could be endangering their health. Now you might be curious, what about outdoor air quality, right? But like we found that almost all participants experience very low exposure outdoors. Although there are a few exceptions. A few people were exposed to pretty high, not too high, I mean, compared to indoor air quality, but some like PM 2.5 concentration ranging from like 46 to 356 while idling at a traffic light with windows open, and or when they were walking around their neighborhood when their neighbor was burning waste, or like when they are attending a bonfire with outdoor grilling. So they told us that many Mexicans frequently participate in bonfires because this is the way they socialize, an important part of a Mexican culture. So finally, to test if there are any difference in scores in knowledge, attitudes, perceptions, and behavioral intention and practice between pre and post session surveys, we performed a series of paired sample t-tests. And we found no significant difference in the knowledge of potential sources of air pollution and possible health effects between pre and post sessions. Maybe using a portable sensor may not directly lead to improved knowledge of the health outcomes associated with air pollution if people didn't experience exact symptoms during exposure. And not all sources that participants identified, like hair dryer, was not actually listed in the survey. Maybe that's why. But we found a significant increase in attitude and perception scores. So after the portable air pollution sensor, people reported being more aware of the air pollution in their surroundings and worrying more about the effect on their health. We don't have much time, right? So right. Quickly, and also we found there's a significant increase in behavior, intention, and practice score as well. More detail, if this is published, maybe. Yeah, so that's one. Yeah, so this study represents a significant step in understanding the effect of places and activities on personal exposure and the role of play a personalized risk information in changing people's perceptions and behaviors. And like all the stuff I put here, but I want to at least leave at least 4 minutes for questions. So let me stop here because I have to leave it. Yeah,
I know, Dr. Park, you're close. We do have time for one question. I don't have any in the chats. Is there any out in the anybody want to pop on your microphone and ask a question? Tarini writes a very interesting study. It made me think about the sources of pollution in my home. Thanks for sharing. Dr. Park, can you think of any like theories that might emerge from this study? You know, one of the simple ones that I got out of your analysis was that I always think about air pollution being outside, and it looks like inside is far more concerning than outside.
Mhm. Okay.
Have you, do you think you'll be able to draw any sort of theories from this work?
Theory. Because I've only tested this, I've only conducted this research in like a kind of like a rural and suburban communities, right? So before I develop a theory, I want to test this in like more like urbanized areas. Actually, like I'm collaborating with someone at in Purdue University, and he's collecting data in a city in California. So, and if we compare like whether it's still people are exposed to indoor air pollution worse than outdoors, then it'll be interesting result. So I want to compare between different areas first.
Well, this is a fascinating story, and I know you need to take off. So I'd like, on behalf of CAGIS and students and faculty at UNC Charlotte, thank you so much for giving us your time in this great presentation. Thank you.
Thank you so much for the opportunity.
Thank you,
And
Yoo Min. Thank you so much.
And I'm sure that anybody, if questions emerge after this, please don't hesitate to call me, and I'll forward any of these to Dr. Park. Thanks again, all. In a couple of days, you'll be able to see this video on our CAGIS website. Look there, you'll see a link to our YouTube channel. Thanks again, everyone.
Thank you, Doug.
Thank you.
Thank you so much.
Thank you.
Thank you.
Wow, many people actually.
Yeah, great. Great work.
Thank you. Bye.